Hi everybody. I wanted to review what we covered in class on Wednesday so that you will be able to understand the idea of definite integrals that appears in the next video. This video will add some more information to what you learned in class about area sums or Riemann sums, including an example of using area to solve motion problems. So please take the time to watch this video, even if you felt comfortable on Wednesday. The problem that we want to solve is this. How do we find the area of a region? As we saw in class, we can answer this question easily if the region is a simple shape, such as a rectangle, a triangle, or a semicircle. But if our region is bounded by a parabola, we have no simple formula for its area. Our solution will be to estimate with rectangles. In practice, we'll use a small number of rectangles. That makes our computation easy, but our answers will be crude. But when computers solve the same problem, they can use a very large number of rectangles. The computations are intense, but that's what computers do best, and so their results are usually good to 4 decimal places or more. Here is a typical kind of problem. Find the area of the region enclosed by the graph of y equals sine x and the x-axis on the interval 0 to pi. We will estimate with rectangles, and we will follow this procedure. First, we will choose n, the number of rectangles. In our case, we're going to choose n equals 3. This nice small number makes our computation simple. A calculator would choose something like n equals 10,000. Second, we're going to choose the width, delta x, of our rectangles. The best choice for most practical purposes is to make the rectangles equal width, so that we can compute delta x equals b minus a over n. It is possible to choose the rectangles to be of different widths, but you should have a compelling reason to do so. In our problem, delta x equals pi over 3. After we have chosen our number of rectangles and calculated our width, we're going to partition our interval. The way that we do this is to start at the leftmost value of x and go up in multiples of delta x. If you do it correctly, then you should end up at the rightmost value of x with the correct number of rectangles. So in our case, since delta x is equal to pi over 3, we start at x equals 0 and count 0, pi over 3, 2 pi over 3, and 3 pi over 3, which is pi. Now we're going to choose the heights of our rectangles. As we saw in class, there are several ways of doing this. The 3 most useful choose particular c values in each subinterval. The left rectangular area method chooses each c to be the leftmost point in its subinterval. The right rectangular area method chooses each c to be on the right of its subinterval. And the midpoint rectangular area method chooses each c to be the midpoint of its subinterval. Each one of these choices is very common and very useful. In addition to those 3 methods, there are 2 methods that are used to check the accuracy of our estimate, and those are the upper sum and the lower sum. For the upper sum, each height is the maximum value on its subinterval. You can see in the graph that each rectangle covers the entire area. For the lower sum, each height is the minimum value on its subinterval. In our particular case, that gives us 2 rectangles that have 0 height. Having chosen our n, calculated our delta x, and partitioned the interval, and chosen a method for the height, now we need to write the Riemann sum and calculate it. We're actually going to do that for all 5 of our area methods so that you can see the similarities and differences between them. If we choose the left rectangular area method, then we write area is approximately equal to the sum from I equals 1 to 3 of f of c sub I delta x sub I. Now our delta x is the same for each rectangle, it's pi over 3. And our c sub i's, since we're choosing on the left, are 0, pi over 3, and 2 pi over 3. So we write out the Riemann sum as pi over 3 times the sine of 0 plus pi over 3 times the sine of pi over 3 plus pi over 3 times the sine of 2 pi over 3. Calculating it gives us the final total area estimate of 1.8138. The right rectangular area method is very similar, except that our c sub i's are chosen on the right of each subinterval. So they are pi over 3, 2 pi over 3, and pi. Since the delta x is the same for each subinterval, it makes sense to factor that out of the computation, and I've done so in this one. Interestingly, the result that we get for the right sum, 1.8138, is identical to the result that we got for the left sum. And that happened because our curve was symmetric. Curves that lack symmetry generally will not have the right sum and left sum the same. Now we come to the midpoint rectangular area method, which is slightly tricky because each c sub I is the midpoint of its interval. In our case, that gives us pi over 6, 3 pi over 6, which is the same as pi over 2, and 5 pi over 6. Again, we factor out the delta x of pi over 3, and our final estimate is 2.0944. Take a look at this graph, and then go back and take a look at the two previous graphs, and try to guess as to which of these estimates is a better estimate for the area. Now we come to the upper sum. The upper sum has a slightly different flavor from the other three, because instead of choosing the c sub I in a systematic way, instead I go to each subinterval and I ask, what is the highest y value for this subinterval? So if you look at the graph, on the subinterval 0 to pi over 3, you can see that the highest value is right there at x equals pi over 3, and the y value that corresponds to it is sine of pi over 3, which is root 3 over 2. But then on the next subinterval, pi over 3 to 2 pi over 3, the highest y value is clearly 1. And then finally on the last subinterval, the highest y value is sine of 2 pi over 3, which is again root 3 over 2. So, choosing those y values, the highest ones, we construct our sum as we did before and get our value. The lower sum is very similar to the upper sum, except that instead of choosing the maximum height, we choose the minimum height for each subinterval. In our case, this gives us a somewhat amusing result, because the lowest value of f of x on the interval 0 to pi over 3 is actually 0, so we end up with a rectangle of 0 height and therefore 0 area. The same thing happens on the interval 2 pi over 3 to pi. The lowest height is sine of pi, which is equal to 0. So, the only contribution that we get to area comes from the middle rectangle, which has a minimum height of root 3 over 2 at x equals pi over 3. Constructing the lower sum, we get the result, which is that the lower sum is 0.9069. Before we move on, take a moment to go back and compare and contrast the 5 methods that we have for determining heights of rectangles. These are the 5 most commonly used methods by mathematicians and scientists. They're not the only methods, but they are the most commonly used ones. Statisticians will sometimes compute areas by doing what's called a Monte Carlo method. They actually pick a random value in each subinterval. So you can see that there's a lot of possibilities out there, but the 5 that we have are the ones that we're going to use. One of the things I hope you noticed when you compared and contrasted the methods was that the upper sum and the lower sum were not very accurate, and that's actually by design. The upper sum and the lower sum are designed to be the worst case scenarios. The area is guaranteed to be greater than the lower sum, and it is guaranteed to be less than the upper sum. So this is an important idea. called the Riemann sum bounding principle. Any Riemann sum that you can construct with any partition and any choice of C sub I is guaranteed to be trapped between the lower sum and the upper sum. So let's recap what we've done so far. Riemann sums are used to compute areas. We construct them by first choosing an n, then computing delta x equals b minus a over n, partitioning our interval, and then choosing the heights of our rectangles with a left sum, a right sum, a midpoint sum, or rarely an upper or lower sum. And then finally, having done all that, we set up and calculate our sum. Area is approximately equal to the sum from I equals 1 to n of f of c sub I delta x sub I. One of the questions that we did not consider in class is this: what happens if f of x is negative in some part of the interval that we're constructing an area sum over? Well, it's pretty clear that if f of x is negative, then it's going to give us a negative value for the area of its rectangle. What does that mean? Well, it doesn't mean that the rectangle has actual negative area. Instead, it simply means that the Riemann sum computes the opposite of the area for that region. We call this net signed area. Signed because the sine of the area of the rectangle corresponds to the sine of f of x, and net because when we add together the positives and negatives, they net out to give us a grand total. Let's finish with a nifty example that illustrates the power of Riemann sums for problem solving. Consider this problem. A particle moves along the x-axis with a velocity given by v of t equals sine of t for t greater than or equal to 0, with t in seconds and v in meters per second. Estimate the displacement of the particle from t equals 0 to t equals pi seconds. Well, this problem is one that we know how to solve already. It's just an antiderivative problem. We are given the velocity, and we're trying to find the change in the position. So we can immediately write s of t equals the antiderivative of the velocity equals negative cosine t plus the obligatory constant c. And delta s is therefore equal to s of pi minus s of 0, final minus initial, which in turn is equal to negative cosine pi plus c minus negative cosine of 0 plus c, which is exactly equal to 2 meters. But now let's pretend for a moment that we don't know how to anti-differentiate our velocity. We could use a different method. The second solution relies on something that you learned in the 6th grade. Distance equals rate times time. Or to put it in our terminology, the displacement delta s equals velocity times the time delta t. Here, we have a constantly changing velocity, so we cannot directly apply the formula distance equals rate times time. But we can do this. We can divide up the time interval 0 to pi into smaller time intervals. And for each one of those time intervals, we can choose a representative velocity. Then we can use distance equals rate times time to compute the displacement for each time interval, and then add up to get the total displacement. But now when I write in math the process that I just described, something wonderful happens. My displacement is equal to the sum of rate times time for each time interval. In other words, it is the sum from I equals 1 to n of velocity times delta t. That's a Riemann sum. And in fact, because our velocity is sine of t, which is a function that we were working with earlier, we've actually already computed this Riemann sum for every single one of our methods. So if we choose the midpoint method, for example, then we get that delta s is equal to pi over 3 times 1/2 plus 1 plus 1/2 is 2.0944 meters. So the Riemann sum, the area actually computes the displacement. That is a remarkable thing. Now, because we already had our first solution, you might not be very impressed with our second solution. It did take more computation. But it's not too hard to imagine that our velocity v of t could have been something without an obvious antiderivative. It could have been something like v of t equals e to the negative t squared, or even something much more gross than that. In fact, in scientific contexts, our velocities have no formula whatsoever. We just have data points. And so in those cases, solution number 2 is our only hope. But also, solution number 2 suggests to our minds a really interesting idea. The net signed area under the velocity curve is the displacement. And the antiderivative of the velocity is also the position. And this suggests that there might be a really deep connection between areas and antiderivatives. We will study that connection next week. Take care.